Thank you for joining me today. In this video, I will go through a few examples, but before doing this, I would like to remind you what we covered in the previous videos. We covered if we have member like this one and supported from one side, and we have applied force, tension, or maybe the applied force is compression, whatever. This applied force, in this case, which is tension, pulling the member, will cause elongation, delta L. Or if we have compression pushing the member, we will have contraction, delta L. This delta L will equal the applied force times the original length of this member, or this member, original length, divided by A, the cross-section area of the member, times E, Young's modulus of the material of this member. Does that make sense? If we have many members connected together, like this one, and this one, and this one, and we have applied force, the final elongation or the final contraction at the free end here will be summation for P times L divided by A E for each part. We have this part number 1, we have this part number 2, we have this part number 3. So you have to figure out what is the force in each part, what is the length of each part, what is the cross-section area of each part, and what is the Young's modulus of each part. Does that make sense? We have an example here. We have this shaft, or this two parts of the shaft AB and BC between two walls, wall number 1 and wall number 2. And we have applied force P equal 15 kilonewton. We need to determine the support reactions at the rigid supports A and C. And then we need to figure out what are the stresses in part AB and part BC. The Young's modulus of the material of the shaft equal to 100 gigapascal. So from engineering mechanics, I believe this applied force P trying to move point B to right. So I believe I will have a reaction at C in the opposite direction, and the reaction at A in the opposite direction. So this reaction at A, and this is the reaction at C. However, you can assume any direction, it's up to you. But I imagine the applied force 15 kilonewton moving to right, so I expect the reactions at A and C will move to left. If you did not assume this, it's up to you. Go ahead and assume what you want. From engineering mechanics also, if you apply summation f of x equals 0, I believe negative RA, positive 15, negative RC will equal to 0. So I can say the reaction at A plus the reaction at C will equal 15 kilonewton, and this is equation number 1. Does that make sense? This is the equation number 1 from engineering mechanics. Then let's talk about the axial elongation or axial deformation in each part. Let's start with part AB. What is the length of part AB? What is the cross-section area of part AB? What is the Young's modulus of part AB? What is the applied force in part AB? Then I can tell you what will be the elongation or the contraction or the axial deformation of part AB, which equal PL divided by AE. This is for part AB. So first of all, the length of part AB equal 600 millimeter. The cross-section area of part AB, we have a diameter equal 50 millimeter. So by divide 4 times this diameter square will give you the cross-section area of this part. By divide 4 times 50 square will give you 196 point, I'm sorry, 1963.5 millimeter square. Let me check it one more time. Yes, 1963.5. The youngest model for the material, it will be 200 gigapascal, or you can convert it to be 2000 megapascal, which is Newton per millimeter square. The applied force in part AB looks like I am going to make cut in this part, anywhere. Excuse me. Anywhere. Then we have two options. You can use the left part or you can use the right part. It's up to you. For me, I'm gonna use the left part, which is the smaller part. So we have here the left part. At this end, we have reaction RA. At this cut, if you apply summation f of x equals 0, I should have a reaction here RA opposite to this reaction, and this RA to make sure the summation f of x equals 0. And this force RA will cause pulling tension. That makes sense? It will cause tension. So the applied force will be RA tension. And I decided RA will be in kilonewton, RC in kilonewton because 15 in kilonewton. So this force in the part AB in kilonewton. Then I can say the elongation or the axial deformation in part AB will equal the applied force in this part RA time 1000 to be in Newton, time the length of this part 600 millimeter divided by the area 1963.5 time the Young's modulus 200,000 Newton per millimeter square. Looks like your units are consistent. This one in Newton right now, this one in millimeter, this one in millimeter square, this one in Newton per millimeter square. So everything in millimeter and Newton. I can tell you what is the expected axial deformation in this part. It will be a function of reaction RA. This value equal 0.00153 RA, and this is there will be elongation. Elongation means positive because the applied force in this part is tension. Does that make sense? Let's do it one more time for part BC. For part BC. What is the length of part BC? What is the cross-section area of part BC? What is the Young's modulus of part BC? What is the applied force in part BC? The length of this part BC equal also 600 millimeter. The diameter of part BC is 25 millimeter. So the area will be pi divide 4 times 25 square will give you an area equal pi divide 4 times 25 square. will be 490.87 millimeter square. Young's modulus for the same material 200 giga Pascal, which is 200,000 mega Pascal, which is Newton per millimeter square. To figure out the applied force in this part, I'm gonna repeat what I did. I will do cut in part BC. This cut will divide your structure to two parts, part on the right and another part on the left. I'm gonna use the smaller part, which is more easy, so I'm gonna use the right part. If you used the right part, I have here a reaction coming to this way, RC, this one, and I did cut here. So if you apply summation f of x equals 0, I must have another force in this way to make sure the summation f of x equals 0 and will equal RC. This force is pushing your part of the shaft, so it will be compression. Compression means we will have negative value for the force in this member or this part BC, kilonewton. Compression. That means the delta in part BC, delta L, will equal the applied force time L divided by AE. This elongation, this axial deformation will be contraction. Contraction means negative. Negative RC, the applied force time 100 to be, 1000 to be in Newton. The length of this part equals 600 millimeter. The cross-section area of this part is 490.87. The Young's modulus of this part 200,000 megapascal. Everything in Newton, everything in millimeters, so the final value will be negative 0.00611 RC. So by the end, I figured out how much elongation expected in this part AB, how much contraction in this part BC. Keep in your mind, the total shaft AC will not elongate and will not contract. Do you know why? Because we have two rigid walls. We have two rigid walls. Will not allow for any movement at A or any movement at C. That means if you add any axial deformation in this part plus any axial deformation in this part must equal 0. Because the total change in the axial deformation for the whole shaft will be 0. So I can say the two rigid wall will prevent any axial deformation in the whole shaft. No way for any axial deformation. That means the axial deformation that happened in part AB, which is 0.00153 reaction at A, plus the axial deformation that happened in part BC, which is negative 0.00611 RC, must equal 0. No way for any axial deformation in the whole shaft, because we have two rigid walls at A and C will prevent any contraction or elongation or any axial deformation in the whole shaft. So what happened in part AB plus what happened in part BC must equal 0. So this one will give you another equation for RA and RC. From this one, I can say RA will equal for RC. What happened? I moved this part to the other side, so RA will equal 0.00611 divided by 0.00153 RC. So we'll give you RA equal 4 RC. I moved this term to the other side, then divided by this number 0.00153. So to find the value of RA as a function of RC. Please go back to the first equation that you set up from engineering mechanics. RA plus RC was equal 15. So I'm going to remove RA and put 4 RC. So 5 RC will equal 15. The only unknown in this equation, RC, will be 3 kilonewton. Once you get the value for RC, I can go back here and put the value of RC equal 3. So the value of RA will equal 12. Does that make sense? So the final conclusion, here is your shaft. Here is end A. Here is the second part of the shaft. Here is end B, C. This one is B. This one is C. We have a force here, 15 kilonewton. I found the reaction RA equal 12. So I will have a reaction here equal 12. And you found this reaction positive. That means the assumed direction for RA is correct. RC is positive. You found it positive, 3 kilonewton. That means the assumed direction for RC that you assumed to left also equal 3 kilonewton. This is the final reactions at A and C, and this is the first part of the problem. We need to figure out the support reactions at the rigid supports A and C. The second part, what are the stresses in part AB and part AC? So stress in part AB will equal the applied force in this part, which is tension 12 kilonewton. I'm gonna multiply it by 1000 and divide it by the area of this part, 1963.5 Newton per millimeter square. This will be the stress in part AB. 12,000 divided by 1963.5. So the stress will be 6.11 megapascal. And this one will be tensile stress. The stress in part BC, keep in your mind, the force in this part will be compression based on this reaction. So it will be -3. I'm going to multiply it by 1000 to be in Newton because it's in kilonewton right now, divided by the cross-section area of this part. The cross-section area of this part is 490.87. So the stress will be negative 3000 divided by 490.87 equal negative 6.1 megapascal, which is compressive stress. That makes sense? So we figured out what are the reactions and what are the stresses in the two parts. We have one more example. Looks like the same example, but we have a little bit change. We have a shaft under the effect of a force 20 kilonewton at this point C, and this shaft is only supported at A, and we have a gap we have a gap of 0.2 millimeter between the end of the shaft and the second wall. So far, we don't have any contact between the end of the shaft and the wall. And I expect this 20 kilonewton will cause elongation in this shaft. So maybe the end of the shaft will hit the wall and maybe not. So we need first to check if the end of the shaft, we need to check if the end of the shaft is hitting the wall at B. How can I do this? We have two parts, part AB, part AC and the part CB. Part CB will not have any change in the axial deformation because PLAE will be 0. Do you know why? Because the force P equals 0. If you look to this part, I will decide to use the right part. So the right part looks like this. Keep in your mind, we don't have, I'm assuming we don't have any contact between the end of the shaft and the wall. So we don't have any force. That means at your cut, we will have 0 force. If you have 0 force, P equals 0, so the axial deformation in this part will be 0. But for AC, if you did cut here, so here is the end of the shaft, and this is the collar at C, and we have a force here 20, and I did cut here. Keep in your mind, we don't have any contact at the end of the shaft. So for equilibrium and summation f of x equals 0, the force at this cut will be 20 kilonewton. So we will have PL divided by EAE. For this part, the applied force will be 20 times 1000 to be in Newton. The length of this part, AC, equal 400 millimeter. The cross-section area of this part with a diameter 10 millimeters, so pi divide 4 times 10 millimeter square. The Young's modulus of the material is 200 gigapascal. It will be 2000 megapascal. So the elongation, so first of all, I'm assuming there is no contact between the end of the shaft and the wall at B. In this case, we will have only force in part AC equal 20 kilonewton. And we don't have any force in part CB because we don't have any contact so far with the wall. In this case, the elongation that happened in part BC will be 0, and the elongation in part AC will be 0.5 millimeter. Wow. So the elongation, the final elongation in the shaft will be 0.5 millimeter. However, this elongation is greater than the gap between the end of the shaft and the wall at B. So your assumption is not correct. The end of the shaft will hit the wall at B. Does that make sense? So we will have a new problem saying this. We have a force here, 12, how much? 20 kilonewton. and we have a wall, and after a little elongation, which is 0.2 millimeter, we will have this wall at B. This is A, this is C. Does that make sense? So only 0.2 millimeter is allowed, and then we will have a reaction here, RB, and we will have a reaction here, RA, like we did in the previous example. But in the previous example, from the beginning, we have direct contact between the two walls and the ends of the shaft. But for this one, unfortunately, I am not sure if this force 20 kilonewton will succeed, to push the shaft to hit the ball at B or not. So I checked it and I found the elongation in the shaft equal 0.5 millimeter, which is greater than the gap at the end. That means the shaft will hit the wall, but will hit the wall after 0.2 millimeter. After hitting the wall, we will have a reaction RB and a reaction RA. Keep in your mind from engineering mechanics, if you apply summation f of x equals 0, we will have negative RA, we have positive 20 kilonewton, we have negative RB will equal 0. So reaction RA plus reaction RB will equal 20. That makes sense? We have two parts. So part AB, the length of this part, the area of this part, the Young's modulus of this part, the applied force in this part. For part AC. For part CB, what is the length of this part? What is the area of the cross section of this part, Young's modulus of this part, and what is the applied force in this part? For part AC, the length equal 400 millimeter. The area equal pi divide 4 times the diameter of this shaft equal 10 millimeter, which is constant for the two parts. So the area will be pi divide 4 times 10 square equal 78.53 millimeter square. Young's modulus 200,000 megapascal. The applied force in this part will be tension reaction RA in kilonewton. That makes sense? For the second part, part CB, the total length of this part, the original length of this part, 800 millimeter. The cross-section area is the same, 78.53. Young's modulus 200,000 megapascal. And the applied force in this part will be compression, the reaction RB in kilonewton. Looks good. So the elongation in part AC equal the applied force RA in kilonewton times 1000. Positive, it's a tension. To be Newton, the length 400 divided by the area 78.53. The Young's modulus 200,000. Your units are good. So point 025 RA positive. The contraction in part CB will equal the applied force negative RB. I'm gonna multiply it by 1000 to be Newton. The length of this part is 800 millimeter. The cross-section area 78.53. The Young's modulus 200,000. The value will be negative, means contraction. Point 051 RB. Keep in your mind any axial deformation in part AC plus any axial deformation in part CB will equal the only allowable gap 0.2 millimeter. So delta in part AC plus delta in part CB will equal 0.2 millimeter. This is the allowable axial deformation in the whole shaft. You know why? If you go back to the problem, if you go back to this problem, any axial deformation in this shaft, the total axial deformation is only allowed to be 0.2 millimeter. After that, this wall will prevent any axial deformation anymore. So once you get the axial deformation in each part, summation of all of them will equal 0.2 millimeter. In the previous example, after you got the axial deformation in each part, the summation of the axial deformation will equal 0 because we don't have any gap. But in this one, summation of the axial deformation for the two parts will equal 0.2 because after 0.2, no axial deformation is allowed. That makes sense? So I can say positive 0.025 RA, negative 0.051 RB will equal 0.2. So this is another equation between RA and RB because we have a previous one. Which one? This one. RA plus RB equal 20. RA plus RB equal 20. So go ahead and solve the two equations together to find out the reactions RA and RB. I think from this one, I can say RA will equal 20 minus RB. Then I will go back to this equation. So 0.025 times RA, which is 20 minus RB, minus 0.051 RB equal 0.2. The only unknown in this equation is RB. So I think I can figure out the reaction RB. It will be just a moment. I can figure it out. So 0.025 plus 0.051 divided by 0.2 minus 0.025 times 20. It will be 3.9 kilonewton. If you go back here and put RB equal 3.9, RA will equal 16.1 kilonewton. So RA, the reaction here, will equal 16.1 kilonewton, and the reaction here will be 3.9 kilonewton. We are looking for the reactions at A and B. But first of all, the first step of this problem, we need to make sure the shaft will hit the wall. So we will have reaction. Because if the shaft did not hit the wall, we will not have any reaction at B, and the whole reaction at A will be 20 kilonewton, and that's it. That makes sense? This is the first step, check. The second step, I figured out. We have reaction at B, we have reaction at A. I figured out what is the axial deformation in part AC, what is the axial deformation in part CB. Keep in your mind the summation of the total axial deformation only allowed to be 0.2 millimeter. After that, we are not allowed for any axial deformation. This is the second called compatibility equation. This one, so I set up two equations from engineering mechanics and axial deformation compatibility. So I solved the two equations together to find out the total reaction at A and at